Why do we need GPUs for AI? How is Nvidia's Digits project a revolution? Why do we need GPUs for AI? We will break down the mathematical functions of a deep learning or AI model. Here is a linear function. We add a nonlinear function. In summary, an AI model chains linear and nonlinear functions. In our example, we write up to 3 layers. In practice, models can exceed 1,000 layers. For example, we can write the LLM function as follows. When you make a request to an LLM in a certain way, you transform your prompt into a vector x. Then, to calculate y with the LLM function of x. To compute y, the number of operations depends on the number of layers, but also the dimensions of x, a, and b. These are not simple numbers, but very large matrices. In summary, the most time and energy consuming operation in AI is the multiplication of a and x matrices, the linear function. This accounts for 90% of the time and energy spent. To solve this problem, it all started in 2010 with the publication of Anatomy of High Performance Matrix Multiplication. As we see in this animation, the naive multiplication of 2 matrices is very time and energy consuming because it requires reading and rereading the rows and columns of the matrices many times. This naive implementation is even more costly as the matrices grow larger. The nature of the operation means that rereading values is slow because the cache memory is useless. Anatomy of High Performance Matrix Multiplication highlights this problem and proposes breaking down the matrices into tiles exactly the size of the fastest cache memory. This is what we see in this animation. Tiles are moved into local memory to distribute calculations across multiple cores in fast and independent local memory. The design of graphics cards or GPUs was adapted from the start to this type of operations, while remaining very flexible for other mathematical operations, such as chaining nonlinear functions. Because even though matrix multiplication is the most costly, it is not the only one. Many other operations are accelerated and chained on the GPU, especially during the training of an AI model. But all AI advancements revolve around this optimization of matrix multiplication that we have. The OpenBLAS library is an implementation of these operations. There are other manufacturers offering this type of accelerators, but today Nvidia dominates and offers a specific programming language for these operations, which is CUDA. AI libraries have been written in CUDA. Research labs are exclusively equipped with Nvidia GPUs, so new algorithms are written in CUDA. Other accelerator manufacturers are still lagging. Porting AI models to other hardware still takes time. Nvidia GPUs, especially those from Nvidia, are constantly advancing. Why distinguish GPUs from CPUs? An electronic chip can house a limited number of transistors and logic. This quantity can be used according to 2 opposing philosophies. For GPUs, it's about creating as many cores as possible with specific memory management. But each core is simplified to the maximum to perform basic instructions without code anticipation. Whereas the CPU philosophy is to create sophisticated cores for very advanced code execution anticipation. This consumes more logic and allows for fewer cores. We see in this animation a CPU server connected to 4 GPUs via PCI buses. Today, such a server can hold up to 8 GPUs. We see that the core architecture is different in CPUs and GPUs. During the training of an AI model or during its inference in production, the CPU acts as the conductor, loading models and transferring them into GPU memory. Several points are critical in this system. Indeed, it is scalable, but it has several major flaws. PCI links are limited in bandwidth. Loading an LLM from SSD storage is a costly operation, especially since cloud providers often offer SSDs with limited bandwidth when an LLM's parameters are loaded into CPU memory. Another problem is transferring the A and B matrices into GPU memory. If your resources are limited, you can use consumer GPUs with 24 GB of memory. but your server cost will approach $10,000. If you have more significant resources, you can use professional GPUs up to 141 gigabytes of memory, which will cost you over $100,000. If your GPU memory is limited, even with parameter quantization, an LLM cannot be fully loaded into GPU memory. Don't rely on the PCI bus to load parameters gradually. The PCI bus speed is a bottleneck. You will need to distribute the LLM layers across multiple GPUs, which can take time to load GPU memory with parameters. Finally, to compute the final Y from an X, it will need to be transferred to the first GPU. Then propagate the intermediate Y vectors between GPUs via PCI, knowing that they represent much less data than the parameters. Nvidia's Digits project aims to solve this problem. The architecture of Digits follows that of previous Jetsons. That is, it eliminates PCI buses and unifies memory. CPU and GPU core architectures are unified on the same chip, accessing the same memory. We can understand that with 128 gigabytes of unified memory, it will simplify AI development and operations. For researchers, developers, and SMEs, 2 digits could be connected by a fast link similar to PCI. Thus, with the technique we know, the most large-scale state-of-the-art open-source models could be used in inference. This way, SMEs could gain more autonomy and sovereignty through open-source AI. This strategy allows Nvidia to democratize AI hardware, while keeping prices high on professional GPUs, as high scalability of digits cannot be assumed. In a way, it's the same architecture as current Macs. The announcement of the new digits in a mini PC format sounds like a competitor to the Mac Studio. The difference is that Macs have the OS and popular applications we know, but the GPU core programming language is Metal and is not compatible with CUDA. Compatibility with Metal for AI models trained with CUDA coming out of labs can be a challenge. Whereas Digits, it's the opposite. They have CUDA compatibility, but have gaps regarding the OS and applications. The foundation of Digits is a candidate for a new PC architecture similar to Macs, with possible variations in the form of laptops. The future will tell which major players might partner with Nvidia to offer an alternative to Macs, with state-of-the-art open-source models directly executable locally. In the meantime, the winning combo for AI developers in late 2025 could be a MacBook Pro and its digits behind your fiber optic box. See you soon in the next video.